Okay, on this worksheet, 33-1, we're looking at electric fields, okay? Electric fields, if you recall, is just a fancy word for a what kind of field? Starts with an F, a force field, okay? Except it's not a force field that you're used to in everyday life, because usually electric fields are invisible to the human eye, and you don't notice electric fields all around you because usually electrical charges are, you guys remember? They are balanced out, right? Neutralized. So in other words, like Scott, if your body has 50 billion protons, guess how many electrons you have? Like 50 billion, right? So what's the net charge? Positive 50 billion, negative 50 billion, net charge is a big fat what? 0. So you don't notice the push and pull of those charges. Which kind of force field are you used to? It starts with a G, a gravitational field. That's right. And when you play sports, football, baseball, volleyball, soccer, whatever, it's all about knowing how your body and the ball interacts in a gravitational field. Here, we have a positive source, okay? How do we test the field? We use what kind of test charge? A what? A positive test charge. Will this be attracted or repelled? You guys remember? It's going to be what? Repelled. So what you do is you draw a little arrow. There's already one drawn in to represent that force of repulsion, okay? So what would it look like at point B? It would also look like what? Repelled, right? And I want to keep the arrow about the same length to represent that force. How about at point C? Also which way? Away, right? How about at point D? Same thing. How about at point E? Same thing. How about at point F? Same thing. You see that? Now what if I had a point way out here, this point G? Okay, would it still be away? It would still be away, right? But notice like point G is almost like twice as far away, right? So is the field stronger or weaker the further away you are? It's weaker. In fact, it's going to be like not half as weak, but like 1/4 as weak, right? Because electrical force depends on the amount of charge present according to Coulomb's law, but the distance squared, right? Force equals K, Q1, Q2 over the distance squared. We don't have to worry about this electrical constant. We're not doing the math, but Q is for charge and D is for distance squared, okay? So in other words, at G where you're twice as far, the force is only 1/4 as great, okay? So a way to visualize the electric field, okay, this was on the computer lab. This was on the part with the electric field hockey here, okay? And notice, how do we test the field strength? We use what kind of test charge? A what? A positive. And with a positive source, the field is always attractive or repulsive. It's pushing it away. You see that? And notice that the closer you get to the source, see how the force is stronger? And the further away I am, the weaker it gets, okay? And in real life, you don't really like play hockey with charges in the sense that, you know, you play hockey with a puck, but you can think of it like a hockey puck there, okay? And when engineers are designing electrical components like your cell phone or those really cool iPods, it's all about getting charges, woo, to go where you want them to go, woo, so you like score a goal and all that. Very exciting there, okay? Good. Moving down, okay? Looking at what's going on. Next question, C. It says electrical field strength varies as the force on the test charge. So field strength twice as far from the positive charge would also be what? Will also be quarter as great. It's just another way to say that, okay? That using Coulomb's law, you can figure out the force, but an electric field is based on Coulomb's law. That's all. Okay? Now, we're going to do the same thing, but now our source is not positive. It is now what? It is a negative source. So what kind of test charge do you use? A what? A positive test charge. So what kind of force would I feel at point H? A repulsive force or a what? An attractive force, okay? If you're a big fan of Star Wars, okay, this is like when Luke Skywalker or the Jedi Knights go whoosh, like that, and they can like pull like the robots toward him or like grab their lightsabers or whatever, okay? Or like Harry Potter, you know, Levioso, right? Kind of like an attractive force here, right? Okay? So at each of these points, if they're the same distance, the force should be the same, okay? So we represent that with an arrow. That's all, okay? And so this is a attractive force, right? Okay? Yeah, so that was an excellent question. A vector is simply an arrow that represents size and direction. In this case, it's a force vector. Okay, so in other words, like if we were a positive test charge here at point H, okay, it would feel a force attracted towards the negative source, and the length of that arrow represents the force. So all it is a way to visualize anything with size and direction. So why is this useful? That's a great question. Go ahead and flip over to the back side now. Okay, on the back side, there's a lot of directions trying to explain what's going on when you have more than one charge. Let me just show you, because I think you'll understand better. Notice on the left, what kind of source do we have? We have a what? A positive source. On the right side, we have a negative source, okay? So the question is, well, now what happens when you have more than one source? Well, if I look at my test charge at point A, what kind of test charge do we use, guys? A what? A positive source, okay? All you have to do to figure out what happens when you have more than one charge is think about what each one would do individually. So this positive source does what to my positive test charge? It pushes it away, right? What does this negative one do? It sucks it which way? Down, right? See how it sucks it down? So the net effect is this one's pushing up and away, this one's sucking it down and to the right. So the net effect is you can draw what's called a parallelogram. You make a little rectangle, okay? And your final force goes towards the corner of that rectangle, and that's already drawn in for you. So why don't we do point B? We do point B. So what's going to happen at point B from this positive source on the left? It's going to be attracted or repelled. You tell me. It's going to be, which way, guys? It's going to be repelled. So I'll draw my force vector arrow there, right? How about this negative one down here? It's going to be what? It's going to be attracted to this source. Okay, I'm going to draw like a straight line to kind of help me visualize that. So it's going to be like that. And should I make this arrow longer or shorter than my first arrow that I drew? Should be shorter because I'm further away, right? So notice this red vector represents the positive force of repulsion going pretty much straight up. This blue arrow represents the negative force of attraction, the electrical field from that negative source. So the net effect is I'm going to sketch in what's called a parallelogram. You guys know what a parallelogram is? It's simply it's like a rectangle, except it's not 90 degrees. It's a four-sided quadrilateral where the opposite sides are parallel to each other, okay? And then the resultant force points towards that opposite corner, okay? So in other words, this is what's going to happen, okay? I'm going to call this my force, my resultant force, FR. So in other words, this charge here normally would just fly straight up, but because there's a negative source, it's getting sucked over to the right here. Okay? How about we do the last one together? Because this is kind of weird for you guys, right? How about at point C? What would happen? Well, first, this guy, the positive source, is going to do what? Attract or repel? It's going to repel. So let's go ahead and sketch that in. Okay? Just like that. What's this negative going to do here? It's going to do what? It's going to attract it. Okay, so I'm going to go ahead and sketch that in also. Okay, and since they're about the same distance, I'm going to draw the arrows about the same length, yeah? And if we wanted to, we could do a lot of math to calculate exactly how much force is there, but we're not going to worry about that. Now we're going to go ahead and sketch in our parallelogram where the opposite sides of this four-sided figure are parallel to each other, and your resultant force then just points to the opposite corner. So in other words, this thing is getting pushed down and to the right and sucked up and to the left. So the net effect is, or to the right rather, net effect is a positive test charge here would pretty much fly to the right there. Okay? And when you sketch in all these lines and you connect those force lines, that's why you see the field lines flow in that curvy pattern. And that's a pattern you see in nature a lot. It's called a dipole pattern. You see those in magnets and in charge pairs. Okay? Maybe the way to visualize that is back to our electric hockey field simulation, okay? If I have a positive source like we had on the left here, notice how it's always pushing it away, right? And what does a negative source do? Negative source is going to attract it, right? And so see how the field lines flow away from the positive source and towards the negative source, right? And how do you visualize it? Because you have two or more charges, you just think about each field individually and then you add them up as vectors, okay? So in this case, this one's kind of silly because it's just getting pushed away and sucked towards the positive and then towards the negative. And again, if I shift this down so we could look at the field higher up, okay? This is like what we did at point B. See how it's getting pushed away and then pulled down? So the net effect is it's going to go more towards the right, yeah? And then at the last point, at point, we tested a point in our field further down, okay? So I'll go ahead and shift these charges up, okay? And see how the positive source is pushing away, the negative is attracting, so the net effect is we pretty much fly to the right there to see what's going on. Okay? And in real life, that's what we try to do, is design a field of charges, whether it's in your digital camera or your cell phone or your iPod, okay, to get charges to flow where we want them to. And it's the power of the electric field. So on your test tomorrow, on your quiz, okay, these are like some example problems you would have, okay? Says, using your knowledge of electric fields, find the direction strength of the field for each of the following cases at point A. So, for example, here I have a positive source. What kind of test charge do we use? A what? A positive test charge. So which way would the field point? It'd point north what? Northeast, right? How about in the second case? This is a negative source. So which way would it point? It would point what? Southwest, okay? And so on and so forth. Why don't I skip to a harder one here? Let's do this one right here, okay? So which way would this point? At point A, what would the positive source do? It would push it northeast, right? What would the negative source do? It would pull it what? Southeast. So what would be the net effect there? Can you see this? The net effect is I would just be pretty much sucked to the what? To the east. Does that make sense? Okay? So all we're trying to do is visualize the field at each point. Okay? Let's try another one here, okay? How about this one right here, okay, with two negatives? This is interesting. So you tell me, talk me through it, okay? What's this first negative source going to do? It's going to pull at point A our positive test charge which way? Here's my positive test charge. It's going to suck this one. Actually, this one's just going to go straight south, isn't it? Okay? And then over here, we're going to get pulled what? Southwest, yeah? So the net effect is we're pretty much going, if we sketch in our parallelogram here, we're pretty much going straight south but a little bit to the west. Okay? So we're just trying to sketch in roughly by visualizing conceptually which way the field lines will flow. Okay? Let's do another example. Okay? Lee asked about this one right here. Okay? The one to the left here. So again, what kind of test charge do you guys use? We use a what? Positive test charge. So you tell me, which way will this sucker be pulled or pushed? Okay, it's going to be pulled which way? Yeah, exactly. Towards the source, right? So this will be what? Kind of southwesterly in direction. Okay? Yeah. That's it. Now here, see how I have point A and B? Well, what's the difference? You tell me. At point A, we are what? Closer, right? So is the force stronger or weaker compared to point B? Stronger, right? So this is going to be a strong southwest